Welcome to the second problem solving session on quadratic equations. In the first problem solving session, we have solved total 6 problems. So today we will start with the 7th problem. This is our 7th question. Here we have the equation minus 3 into x minus integral part of x whole square plus 2 into x minus integral part of x plus a square is equal to 0 for a real number a. We are given the information that this equation is not having any integer solution. We then have to find out the possible range of a. First we can note that a is not equal to 0, because if a is equal to 0, then clearly every integer is a solution of this equation, because for x in z we know x minus integral part of x, which is the fractional part of x, is equal to 0. So putting a is equal to 0, we can see that every integer is a solution of this equation. Therefore, we have here a is not equal to 0. Now we substitute x minus integral part of x is equal to fractional part of x in the given equation, and then we obtain minus 3 into fractional part of x whole square plus 2 into fractional part of x plus a square is equal to 0. So we are getting a quadratic equation in fractional part of x. Now since we always want to keep the coefficient of the 2-degree term of any real quadratic equation to be always positive, we write it as 3 into fractional part of x whole square minus 2 into fractional part of x minus a square is equal to 0. Now solving this equation, we will get possible choices for fractional part of x, and they are 2 plus minus square root of 4 plus 12 a square divided by 6. After simplifying, we get this is equal to 1 plus minus square root of 1 plus 3a square divided by 3. Now note that 1 plus 3a square is strictly bigger than 1, as we have a is not equal to 0. So therefore we have 1 minus square root of 1 plus 3a square divided by 3 is strictly less than 0. But we know that fractional part of x is always bigger than or equal to 0. So therefore this cannot be a possible choice for fractional part of x. We can see that 1 plus square root of 1 plus 3a square divided by 3 is strictly bigger than 0. So therefore, if fractional part of x is equal to this, then we can write 1 plus square root of 1 plus 3a square is strictly less than 3, and we know this is also strictly bigger than 0. So from here we get that minus 1 is strictly less than square root of 1 plus 3a square, and this is strictly less than 2. Now squaring the inequality, we obtain 1 is strictly less than 1 plus 3a square. This is strictly less than 4. Therefore we obtain 0 is strictly less than a square, and a square is strictly less than 1. So this is a possible range of a square, and from here we get that a belongs to the open interval minus 1 to 0 union the open interval 0 to 1. So option 3 is correct. Also note that here the open interval minus 1 to 0 union the open interval 0 to 1 is a subset of the open interval minus 2 to 1. And as we are to find out all the possible sets where the values of A lie in, therefore we see that the option 1 is also correct. And since the option 2 and option 4 are disjoint from option 3, that is the set open interval minus 1 to 0 union the open interval 0 to 1, we can directly conclude that option 2 and option 4 are not correct. For non-negative real numbers x, let us consider two functions gx, which is given by cosine of x square, and the function fx, which is given by square root of x. We are given here one quadratic equation 18x square minus 9 pi x plus pi square is equal to 0, and two solutions of this quadratic equation are alpha and beta, so that alpha is strictly less than beta. We have to find out the area bounded by the curve y is equal to g compose f of x and the lines x is equal to alpha, x is equal to beta and y is equal to 0. To do this, our first job would be to find out what is alpha and what is beta. Let us do that. The solutions of the quadratic equation are 9 pi plus minus square root of 81 pi square minus 72 pi square divided by 36. After simplifying, we can write 9 pi plus minus 3 pi divided by 36. Now as we know alpha is strictly less than beta, we can write alpha is equal to 9 pi minus 3 pi divided by 36, which means pi by 6, and beta is 9 pi plus 3 pi divided by 36, which means pi by 3. Now note that the function g compose f of x is nothing but the function cosine of x. Now to find out the area bounded by all those four curves, we shall try to draw a picture. Let this be our x-axis and this be our y-axis. Let us write this is x and this is y. And then we draw the line x is equal to alpha. And let this be the line x is equal to beta. Next we draw the graph of the function cosine of x. So this point is pi by 2, this point is pi by 3 and this point is pi by 6. This is y is equal to cosine of x. This one is x is equal to alpha and this one is x is equal to beta. We have to find out the area of the shaded region. As it is very clear from the picture, we have to find out the integral from pi by 6 to pi by 3 of cosine x dx. After integrating, we get sin x from pi by 6 to pi by 3. And solving this, we obtain sine of pi by 3 minus sine of pi by 6, which is square root of 3 by 2 minus half. If we write it in a composite form, this is square root of 3 minus 1 divided by 2. Therefore, we see that here the fourth option is the correct answer. In this question, we are given a region R which contains all pairs of real numbers x, y whose y coordinate lies between x cube and x and whose x coordinate lies between 0 and 1. We are also given a real number alpha in the closed interval 0, 1 so that the line x equals to alpha divides the region R into two equal parts. Then we are given here four options. We have to find out what are all the conditions satisfied by alpha. To solve this, we shall try to first draw the region R. Let this be our x-axis and this be our y-axis. Next, we draw the graph of y is equal to x cube. Then we draw the graph of y is equal to x. I can erase this. Okay. So, this is the point 1. This is y is equal to x cube and this is y is equal to x and this is 0. So, the region I am shading is the region R. Now alpha is a real number between 0 and 1. And the line x equals to alpha divides the region R into two equal parts. So, let the line x equals to alpha be this. So, this point is alpha and this is the line x equals to alpha. We call this region as region A and this region as region B. So, we know that the area of the region A is equal to the area of the region B. Let us first compute the area of the region A. It is very clear from the picture that this is integral from 0 to alpha x dx minus 0 to alpha x cube dx. After integrating, we obtain x square divided by 2 minus x to the power 4 divided by 4 and we have to evaluate this from 0 to alpha and finally we get alpha square divided by 2 minus alpha to the power 4 divided by 4. Next, we will compute the area of the region B and there the limiting value will be from alpha to 1. So, we do that now. This is alpha to 1 x dx minus alpha to 1 x cube dx. So, we have here x square divided by 2 minus x to the power 4 divided by 4 and we evaluate it from alpha to 1. So, we have 1 by 4 minus alpha square divided by 2 minus alpha to the power 4 divided by 4. Now, as we know the area of the region A and the area of region B are equal, then we can equate them and we obtain, I can write it here. So, the area of region A was alpha square divided by 2 minus alpha to the power 4 divided by 4 and here we have obtained 1 by 4 minus alpha square divided by 2 plus alpha to the power 4 divided by 4. Simplifying this, we obtain alpha to the power 4 divided by 2 minus alpha square plus 1 by 4 is equal to 0. Now if we multiply this equation by 4, then we obtain 2 alpha to the power 4 minus 4 alpha square plus 1 is equal to 0. So we are getting a quadratic equation in alpha square. Now if we look at the options here, we can see that third option is correct, that alpha satisfies the third condition. Now we shall check also rest of the options. We have already obtained a quadratic equation in alpha square. I write the equation here again. 2 alpha to the power 4 minus 4 alpha square plus 1 is equal to 0. By solving this, we get possible choices for alpha square, and they are 4 plus minus square root of 16 minus 8 divided by 4, which is 1 plus minus square root of 2 divided by 2. Now we can note that 1 plus square root of 2 divided by 2 is strictly bigger than 1. Therefore, this cannot be a possible choice for alpha square. As we have alpha is less than equal to 1. So, we have alpha square is equal to 1 minus square root of 2 divided by 2. Now, if alpha is less than or equal to half, then alpha square is less than or equal to 1 by 4. Therefore, we get 1 minus square root of 2 divided by 2 is less than or equal to 1 by 4. And from here we obtain that 3 by 4 is less than or equal to square root of 2 divided by 2. Now squaring this we obtain 9 by 16 is less than or equal to 2 by 4, that means half. But we know this is not possible. Therefore, alpha cannot be less than or equal to half. Hence, the option 1 is not correct, and so therefore option 2 has to be correct. So now only we have the option 4 to check. We can see that here the option 4 is a quadratic equation in alpha square. If we solve this for alpha square, we get alpha square is having the possible choices minus 4 plus minus square root of 16 plus 4 divided by 2. That means minus 2 plus minus square root of 5. And as we can clearly see that none of these values agree with the choice of alpha square which we have already got. So therefore, the fourth option is not correct. This is our 10th question. For a positive integer n, let us consider the quadratic equation x into x plus 1 plus x plus 1 into x plus 2 plus up to x plus n minus 1 into x plus n is equal to 10n. We have to find out what is the value of n for which this quadratic equation is having two consecutive integer solutions. Now note that in the left hand side of this quadratic equation there are total n many summands. So we can see that the coefficient of x square is n, Now we have to find out what is the coefficient of x. For that, let us first split the first summand and we get x square plus x. If we split the second summand, we get x square plus x plus 2x plus 2, which is basically x square plus 3x plus 2. And then we split the last summand and then we get x square plus n minus 1 into x plus nx plus n into n minus 1. So here we get x square plus 2n minus 1 into x plus n into n minus 1. So therefore, the coefficient of x is equal to 1 plus 3 plus up to 2n minus 1. Now if we sum it, for summing it, let us add 2 plus 4 up to 2n, and then we subtract what we have already added, 2 plus 4 plus so on so forth up to 2n. So this is nothing but 2n into 2n plus 1 divided by 2 minus, if we take 2 out here, then this is n into n plus 1 divided by 2. So finally we are getting here n into 2n plus 1 minus n into n plus 1. So this is 2n square plus n minus n square minus n. So we are getting this is n square. So the coefficient of x in this quadratic equation is n square. Now we find out the constant term. From the first summand, that is from x into x plus 1, the contribution to the constant term is 0. And from the second summand, that is x plus 1 into x plus 2, the contribution to the constant term is 2. For better understanding, we write the third term, which is x plus 2 into x plus 3. This term contributes 6 to the constant term. Now, the last summand is x plus n minus 1 into x plus n. From here we can see that this term contributes n minus 1 into n to the constant term, and also in the right hand side we have 10 n. So altogether we have, we write it here, 0 plus 2 plus 6 plus up to n into n minus 1, and we had 10n in the right hand side, so this is minus 10n. Now note that this part is already in the form sum of k into k minus 1. K is from 1 to up to n, and this is minus 10n. If we split this one, we obtain k square. K is from 1 to up to n, and this is k. K is from 1 to up to n, and this is minus 10n. So therefore, this is n into n plus 1 into 2n plus 1 divided by 6 this is minus n into n plus 1 divided by 2, and this is minus 10n. Now after simplifying we get, let us first take n into n plus 1 divided by 2 out. This is 2n plus 1 divided by 3 minus 1, and this is minus 10n. So therefore we have here n into n plus 1 into n minus 1 divided by 3 minus 10n. So therefore this is n into n square minus 1 divided by 3 minus 10n. Now if we write down the quadratic equation in a simplified form, we obtain nx square plus n square x, and the constant term is n into n square minus 1 divided by 3 minus 10n is equal to 0. As n is a positive integer, we have n is not equal to 0, so we can cancel n from this equation, and we have x square plus nx plus n square minus 1 divided by 3 minus 10 is equal to 0. So our quadratic equation is x square plus nx plus n square minus 31 divided by 3 is equal to 0. We have that this equation is having two consecutive integer solutions. Let's say m and m plus 1. So therefore we have m plus 1 is equal to minus n. So we have 2m is equal to minus of n plus 1, and so we have m is equal to minus n plus 1 divided by 2, and also we have m into m plus 1 is equal to n square minus 31 divided by 3. Now we substitute the value of m which we have got in this equation, and then we obtain minus n plus 1 divided by 2 into 1 minus n plus 1 divided by 2 is equal to n square minus 31 divided by 3. After simplifying we get minus n plus 1 into 1 minus n divided by 4 is equal to n square minus 31 divided by 3, and this one is nothing but n square minus 1 divided by 4, and the right hand side is n square minus 31 divided by 3. So therefore we have 3n square minus 3 is equal to 4n square minus 124, and solving this we get n square is equal to 121, and as n is a positive integer, we can conclude from here that n is equal to 11. So therefore the third option is correct here. Here in this question we consider a real quadratic equation px is equal to 0. We are told that this equation is having only purely imaginary solutions. That means the solutions are of the form I alpha, where alpha belongs to the set of real numbers. Then we consider the equation p of px is equal to 0. We have to find out what are all the correct information about the solutions of p of px is equal to 0. Let us recall that a real quadratic equation is of the form ax square plus bx plus c is equal to 0, where a is strictly positive, and the solutions are of the form minus b plus minus square root of b square minus 4ac divided by 2a. Now, since it is given to us that the solutions are purely imaginary, then we can conclude that minus 4ac is strictly less than 0. Because since we know that the solutions are complex, from there we first conclude that b square minus 4ac is strictly less than 0, and then next we conclude that b is equal to 0 as the solutions are purely imaginary. Because if b is non-zero, then from here we can see that b would contribute to the real part of the solutions. So therefore we have b is equal to 0. So we have here AC is strictly bigger than 0. That means we have A and C, both of them have same signs. Now we write what is our first equation, Px is equal to 0. So this is ax square plus c is equal to 0. From here we can write this in the form x square plus c divided by a is equal to 0. Let us call c divided by a as some constant c prime. And since a and c both are having same signs, we can conclude that c prime is strictly bigger than 0. Now let us write what is p of px is equal to 0. So this is nothing but x square plus c prime whole square plus c prime is equal to 0. Now let us split this part. After splitting we get x to the power 4 plus 2x square c prime plus c prime square plus c prime is equal to 0. Note that this is a quadratic equation. In x square. So let us solve this for x square. After solving the equation, we obtain minus 2c prime plus minus square root of 4c prime square minus 4 into c prime square plus c prime divided by 2 are the possible choices for beta square, where beta is a solution of p of px is equal to 0. And now simplifying this, we obtain minus c prime plus minus I square root of c prime. So we see that solutions of p of px is equal to 0 are neither real nor purely imaginary, because if beta is of the form say I alpha or beta is of the form alpha where alpha is real, then we get beta square is equal to minus alpha square or beta square is equal to alpha square. But we have already got here that beta square is not real. So therefore, the fourth option, which says neither real nor purely imaginary solutions, is correct. And immediately looking at all other options, we can say that rest 3 options are not correct. This is our question number 12. Here we have 4 distinct numbers a, b, c and d. We have 2 quadratic equations x square minus 10cx minus 11d is equal to 0 and x square minus 10ax minus 11b is equal to 0. We are told that a, b are the solutions of the first quadratic equation and c, d are the solutions of the second quadratic equation. We have to find out what is the sum of a, b, c and d. Let us do that. Since we know that a, b are the solutions of x square minus 10cx minus 11d is equal to 0, we can write a plus b is equal to 10c. And since CD are the solutions of x square minus 10ax minus 11b is equal to 0, we can write c plus d is equal to 10a. So therefore, summing these two, we obtain a plus b plus c plus d is equal to 10 into a plus c. So from here we see that to know the sum of these 4 numbers a, b, c and d, it is enough to know the sum of a and c. Now since a is a solution of the first quadratic equation, we can write a square minus 10ca minus 11d is equal to 0. And since c is the solution of the second quadratic equation, we can write c square minus 10ac minus 11b is equal to 0. Now using these two, we will try to get a relation in a and c. If we subtract the second equation from the first one, we obtain a square minus c square minus 11d plus 11b is equal to 0. That means we are getting a plus c into a minus c is equal to 11 into d minus b. We will now find out what is d minus b. Recall that we had a plus b is equal to 10c and c plus d is equal to 10a. So from here we also get that a plus b minus c minus d is equal to 10 into c minus a. That means we have b minus d is equal to 11 into c minus a. So let us write it in this form. D minus b is equal to 11 into a minus c. Now we substitute this here and therefore we obtain a plus c into a minus c is equal to 121 into a minus c. Now we can cancel a minus c from both sides because we have a, b, c and d are all 4 distinct numbers. So a is not equal to c and therefore a minus c is not equal to 0. So we get from here that a plus c is equal to 121. And hence we have a plus b plus c plus d is equal to 10 into a plus c is equal to 10 into 121. So therefore we have here the fourth option is the correct one. This is our question number 13. Let S be the set of all non-zero real numbers alpha such that the quadratic equation alpha x square minus x plus alpha equals to 0 has two distinct real solutions x1 and x2 with the property that modulus of x1 minus x2 is strictly less than 1. We have to identify the possible subsets of the set S from the list given below. For that, we first recall that for a real quadratic equation ax square plus bx plus c equals to 0, we know it has distinct real solutions if and only if b square minus 4ac is strictly bigger than 0. So using this, we get here one condition that 1 minus 4 alpha square has to be strictly bigger than 0. That means 4 alpha square has to be strictly less than 1. That is, alpha square has to be strictly less than 1 by 4. Now as alpha is non-zero, we are given in the question, we can conclude that alpha has to be in the open interval minus half to half excluding the number 0. Now we use the second condition which is given to us, that the distance between the solutions x1 and x2 is strictly less than 1. That means x1 minus x2 square is strictly less than 1. In fact, this is an if and only if condition. Now we can write x1 minus x2 whole square as x1 plus x2 whole square minus 4x1 x2. Recall that our equation is alpha x square minus x plus alpha is equal to 0. Therefore, x1 plus x2 is equal to 1 by alpha and x1 into x2 is equal to alpha into 1 by alpha, which is 1. Substituting these two values in the inequality here, we get 1 by alpha square minus 4 is strictly less than 1. That means 1 by alpha square is strictly less than 5. That is, alpha square is strictly bigger than 1 by 5. So from here we can conclude that alpha is strictly bigger than 1 by square root of 5, or alpha is strictly less than minus 1 by square root of 5. Now we can write down the set S explicitly. So the set S is equal to minus half to minus 1 by square root of 5 open interval union the open interval 1 by square root of 5 to half. Hence clearly the set given in option 1 is a subset of the set S. Also, the set given in option 4 is a subset of the set S, but the sets given in option 2 and 3 are not subsets of S. Therefore, here the first and the fourth options are correct. Let us now look at this question. Here we have P to be a non-zero number And then we have the quadratic equation px square plus qx plus r is equal to 0 with the property that p, q and r are in an arithmetic progression. We are given that alpha and beta are the solutions of this given quadratic equation with the property that 1 by alpha plus 1 by beta is equal to 4. We have to find out the value of modulus of alpha minus beta. So, since alpha and beta are the solutions of the given quadratic equation, we can immediately write alpha plus beta is equal to minus q divided by p, and also alpha into beta is equal to r divided by p. Since 1 by alpha plus 1 by beta is equal to 4, from here we can conclude that alpha plus beta is equal to 4 into alpha beta. Now we know that alpha into beta is equal to r divided by p. Therefore, alpha plus beta is equal to 4r divided by p. Now equating these two, we obtain that minus q divided by p is equal to 4r divided by p, and as p is non-zero, we can write q is equal to minus 4 into r. So we have got a relation in q and r. Also in the question we are told that p, q and r are in an arithmetic progression. Therefore we can write q is equal to p plus r divided by 2. That means minus 4 into r is equal to p plus r divided by 2, as we have got already that q is equal to minus 4r. This implies p is equal to minus 9r, and hence we have r divided by p is equal to minus 1 over 9. And hence therefore we have alpha plus beta is equal to, we have here 4r divided by p minus 4 divided by 9. We are going to use this relation to find out what is modulus of alpha minus beta. Now we know that alpha minus beta whole square is equal to alpha plus beta whole square minus 4 into alpha beta, and we know the value of alpha plus beta here. If we substitute, we get 16 by 81, and here if we substitute the value of alpha beta, we get this whole thing 4 into alpha beta is equal to 4 into r divided by p, which means minus 1 divided by 9, and hence we are getting this is 16 divided by 81 plus 4 divided by 9, and this is nothing but 52 divided by 81. So therefore we get alpha minus beta is equal to plus minus 2 square root of 13 divided by 9. That means modulus of alpha minus beta is equal to 2 square root of 13 divided by 9, and so we see that the second option is correct. Let us look at this question now. We have three real numbers a, b and c so that a is non-zero. We have three quadratic equations a square x square plus bx plus c equals to 0 and a square x square minus bx minus c equals to 0 and a square x square plus 2bx plus 2c equals to 0. We are told that alpha is a solution of the first quadratic equation and beta is a solution of the second quadratic equation with the property that 0 is strictly less than alpha and alpha is strictly less than beta. Our job is to find out what are the properties satisfied by a solution of the third quadratic equation. Since alpha is a solution of the first quadratic equation, we have a square alpha square plus b alpha plus c is equal to 0 and since beta is a solution of the second quadratic equation, we have a square beta square minus b beta minus c is equal to 0. Let us call fx is equal to a square x square plus 2bx plus 2c. So we have to find out the properties satisfied by a solution of fx equals to 0. We shall first compute what is f of alpha and what is f of beta. F of alpha is equal to a square alpha square plus 2b alpha plus 2c. We can write it as a square alpha square plus b alpha plus c plus b alpha plus c. Now note that we have a square alpha square plus b alpha plus c is equal to 0 as alpha is a solution of the first quadratic equation. So therefore f of alpha is equal to b alpha plus c. And since a square alpha square plus b alpha plus c is equal to 0, so from there we can write b alpha plus c is equal to minus a square alpha square, which we substitute here. B alpha plus c is equal to minus a square alpha square. Since a square alpha square is positive, we get that f of alpha is strictly less than 0. So from here we can conclude that alpha is not a solution of the third quadratic equation. So therefore, if we call a solution of the third quadratic equation by gamma, then gamma is not equal to alpha. That is, we see that the third option, gamma is equal to alpha, is not correct. Now we compute what is f of beta. F of beta is equal to a square beta square plus 2b beta plus 2c. We can note that here a square beta square is equal to b beta plus c. Therefore, substituting b beta plus c in place of a square beta square, we get f beta is equal to 3b beta plus 3c, and this is equal to 3 into a square beta square. So therefore, f beta is strictly bigger than 0. Note that fx is a continuous function and at alpha f is strictly less than 0 and at beta f is strictly bigger than 0. So therefore there must exist a gamma in between alpha and beta so that f of gamma is equal to 0. As we have 0 is strictly less than alpha, strictly less than beta, so we can write there exists gamma which is between alpha and beta so that f of gamma is equal to 0. We see here that the fourth option is correct. Now to check whether the first option is correct or not, let us compute f of alpha plus beta divided by 2. F of alpha plus beta divided by 2 is equal to a square into alpha plus beta divided by 2 whole square plus 2 beta into alpha plus beta divided by 2 plus 2c, and this is equal to a square into alpha plus beta divided by 2 whole square plus b alpha plus c plus b beta plus c. Now since we have beta is strictly bigger than alpha, we can write the first term is strictly bigger than a square into 2 alpha divided by 2 whole square, and note that the second term is equal to minus a square alpha square, and the third term is equal to plus a square beta square. So altogether we are getting this is equal to a square into beta square, which is strictly bigger than 0. So we have f of alpha plus beta divided by 2 is strictly bigger than 0, and this proves that alpha plus beta divided by 2 cannot be a solution of fx equals to 0. So the first option is not correct. Now we need to check only the second option. For that part, let us try to draw a picture. For the purpose of this picture, let us draw only x-axis. Let this be the graph of y equals to f of x. Recall that we have already got f of alpha is strictly less than 0 and f of beta is strictly bigger than 0. Also we have got f of alpha plus beta whole divided by 2 is strictly bigger than 0. Therefore, alpha is somewhere here in this region and beta is somewhere in this region, and alpha plus beta by 2 is somewhere in this region. For simplicity, let us take this point to be alpha, this point to be beta. So alpha plus beta whole divided by 2 will be somewhere here. Now note that alpha plus beta by 2 is strictly bigger than alpha plus beta whole divided by 2, as we have alpha is strictly bigger than 0. So therefore, from the picture it is very much evident that f of alpha plus beta by 2 is strictly bigger than 0. So alpha plus beta by 2 cannot be a solution of fx equals to 0. So the second option is also not correct. We end this session here. We have one more session on quadratic equations. So in the next session we are going to solve some more problems.